Sure.
All right, so Matt Sinclair asks, do you have any insight on why the CPUs perform better at smaller batch sizes and vice versa for GPUs? Or is it just related to the CPUs being latency optimized and the GPUs being throughput optimized, or is it something deeper?
Very good question. So if we look at so on the CPU front, there is a lot of development happening on developing these optimized GEM libraries for the CPUs. And some of these implementations are specific to the particular width of the SIMD unit on the CPUs. Now, if we increase the batch size more, the amount of data that we are going to bring is going to be larger, which means that sometimes the working set size may start exceeding what can be held in the on-chip cache, for example, like the L1 or L2 caches. And that's when you start seeing some of these performance acceleration opportunity to plateau. Whereas on the GPU side, you have a lot more compute throughput-oriented architecture, and so that generally just match well with the more requests that you can pack into a batch. Yeah.
Okay, thank you. So Sour BH asks, what is the data communication you're referring to? Is it from the CPU memory to the GPU memory over PCIe? Or is there a possibility of lossy compression techniques for data compression?
Right, so this is the data communication or data offloading through the PCIe. And for the compression plays a role here, but I guess something that we will have to keep in mind is that recommendation model is very sensitive to any accuracy lost. And therefore, depends on the particular compression techniques, that will be something that we want to pay attention to. Like, what is the trade-off between accuracy, performance, and you know, either bandwidth reduction or sometimes memory capacity reduction. And we've done some of the work in this tensor decomposition space. Instead of storing the information in the raw table format in these embedding tables, what we can do is to replace these embedding table vectors with a sequence of small tensor multiplications. And so that's, for example, a compression techniques that trades off accuracy with additional training time. And I guess the goal here should be we want to be accuracy neutral, or even better, we want to, at the same time, be able to improve the model quality.
Okay, here's a question by me. So, of course, we'd like to facilitate end-to-end optimizations up and down the hardware stack, but how well do we hardware people, or can we hardware people understand DNNs? Like, what changes are possible to topologies without too much accuracy loss? And complemented by, do DNN people understand hardware limitations at all? Like the GPUs have, you know, fairly limited device memory capacity?
Right, very good question, as these are like some of the real world challenges that we actually face when deploying and trying to optimize these DNNs given commodity systems that we have, right? And I think this is where I found at least how system architect can contribute to the solution to like DNN acceleration a lot. So now, if we look at one of the key challenges for training these recommendation models out of box on GPU is exactly this. The HBM memory capacity on GPUs is in tens of gigabytes. And that's obviously not going to be enough to hold these large embedding tables directly. And therefore, they are work in the industry that looks at how do we identify these more frequently accessed part of embedding tables in the GPU memory, and then have the other type of memory as the backstore. And so you find the most frequently accessed embedding vectors in the memories closer to accelerator, either on chip or somewhere, and then store the rest of the embedding tables on the host memory, for example. And now you could also run out of the memory on the host system, and that's when you will have to start distributing these large embedding tables across different CPUs. And so those are also done.
Okay, let's see. Sarva asks, inference workloads requests usually arrive at intervals, making it hard to perform batching, as batching leads to increased tail latency. Is this true even for high traffic scenario of Facebook?
Good question. And also, I think there are some key differences that I will highlight before answering this. So when we look at the traffic coming from, say, web services, right? These eventually get broken down into different application services. So now when we look at these recommendation queries, the kind of arrival rate that we observe could be different from the kind of web queries that come at the front end. However, the trade-off between how much you can queue up and how much queuing delay can we tolerate, there is that problem that we need to balance off as well. The more that we batch, the more likelihood that queuing delay is going to kick in. And therefore, there is the sweet spot as what we talk about in deep Rexes. And so that's the optimal batching degree that we exploited. So for CPUs, that setting is different from if you were having an AI system with a GPU accelerator. And so that's when this identifying the optimal batch size becomes interesting.
Okay, so the next three questions are by Swamit Tanu. So for those of you in the audience, you may not know this, he's a great recent PhD from Georgia Tech who is joining Wisconsin starting in January and is already here. So here's his three questions, one at a time. How frequently do software for recommendation systems change? Are these changes modular and fine-grained, e.g. fine-tuning the feature embeddings, or the changes coarse?
Can I rephrase the question to make sure that I understand it?
Right. You should say a question that you will answer.
Okay. So if I were translating this question, then it will be, when we were designing accelerator, we want to make sure that the hardware innovation cadence would somehow sync up with the software innovation cadence. As if the software is still quickly evolving, then we should probably not be designing application-specific accelerator for this yet, unless there is common set of acceleration operator that we can focus on, okay? Now, if the question is on how quickly is the recommendation models still evolving, then we do see that tons of research is happening in the space, and therefore, at a certain point, if these modeling techniques is going to translate into accuracy improvement, they will be deployed. And therefore, I think this is a trade-off between basically how we want to balance between the kind of accelerator that we put into data center, but still be able to empower the machine learning model designers to explore efficiently model innovation. And therefore, my personal opinion is that there's a space for general purpose processors in this application domain. But then for things that have stabilized, then these are things that can run most efficiently on application specific systems.
Okay, so Swamit's next question is, can we use the insights from recommendation systems to apply to other AI or ML systems, or are these more one-offs?
So is this specifically to the type of optimization?
I'll rephrase the question.
Sure.
So what? Maybe I don't care that much about recommendation systems. You're going to teach me a bunch, but I'll be more interested if what I learned from recommendation systems applies to many other things as well.
Mm-hmm. Mm-hmm. I want to, let me think about this, as I want to come up with a concrete example of how some of these optimization strategies that we identify is beyond the recommendation application domain, okay? So I guess it goes two ways. Let me take this, tensor decomposition work that we are developing, that we are working on right now. I guess the gist of this idea is that instead of storing these values directly in the lookup table, in the embedding table, we want to replace the table lookup with a sequence of matrix multiplication, okay? And so to me, that is something that architects are very good at, actually. It's basically, replacing memory lookup table with computations, okay? But the differences here and the unique characteristic of tensor decomposition technique for the space of recommendation model is that for recommender system, accuracy is really important. And so for other application domain, the accuracy requirement may not be as stringent as compared to recommendation services. And therefore, this will influence how you customize these tensor dimensions. For example, in this particular approach called tensor train decomposition, the rank of the tensors plays a role in training time and accuracy trade-off. And so for recommendation model, we'll spend lots of time to figure out what is the optimal configuration for these tensor decomposition algorithms. Whereas the approach is actually general. It can be applicable to, for example, the language model that also has embedding tables, but it's just going to come with different accuracy, memory capacity, and training time trade-off.
Okay, so we've reached the top of the hour. If anybody feels they need to have to leave, they can leave, but otherwise we're going to continue for those who are interested, like me. Swamit's third question is, any insights on how memory bandwidth / capacity plays a role in designing better recommendation systems? I think you touched on that a little bit already.
Yep. Yeah, I guess the sort of highlight for memory capacity requirement and bandwidth requirement is that these models are only going to grow in terms of size. If we look at across the industry, these embedding tables are now tens to hundreds of gigabytes, and it's not stopping, it's growing into terabyte scale. And memory is expensive. So it's not like we can buy tons of memory to just, to catch up the model size growth, right? We need much better strategies from say architecture optimization space to look at how we can actually store some of these in say SSD, for example, or there's all these like it's basically the general trade-off across latency, memory capacity, and then there's the dimension on cost also. On the memory bandwidth part, they are different mitigation techniques that we are all very familiar with. There are caching, tons of caching strategies that can come and help us out here in order to reduce the memory bandwidth consumption going off chip. And we should build that into system specific for recommendation, for example.
Okay, we have 3 more questions unless more come in, so we're getting there. So KG asks, With Facebook DLRM model, how much quantization accuracy loss, 8-bit integer arithmetic, have you observed compared to floating point, FP16, FP32 model execution?
Cool. So I would like to point KG to this recent work on archive from Facebook. So basically the work is looking at how do we quantize these embedding table vectors to 4-bit without accuracy trade-off. So it is possible, but you have to do it intelligently. And so the work specifically looking at different ways to quantize these embedding tables into lower bit width. And the idea here is that we don't want to make any accuracy trade-off, and therefore there's a lot of efforts going into the work to look at how do you maintain the accuracy requirement while being able to reduce the memory capacity for these models.
Okay. How does he find the paper on archive? You got some keywords or something?
Like email me?
Okay, that sounds good. Email you. Okay, so a couple more questions here from D. Wu. Will the type of parameter server influence the training performance on CPU or GPU a lot?
Okay, will the type of parameter server influence training performance on CPU or GPU a lot? Let me see. So this question is talking about training recommender systems, and as what I've mentioned briefly, because of the large embedding tables, for a lot of these large recommendation model, we currently train on, we use multiple CPUs to hold these embedding tables and train them on a cluster of CPUs. We are also looking at how to leverage the GPU clusters that we have for training these recommendation model. And therefore, what this means is that for example, we can leverage the frequency access pattern for these embedding tables to decide what kind of embedding tables that we want to put onto GPUs, such that we can train both the FC as well as the embedding tables on the GPU, right? Now, and we can do that even better. We can then identify which portion of the embedding table can fit into the GPU memory. And therefore, we don't have to go to the CPU host memory as much. And therefore, I guess the short answer to the question is yes, the type of trainers that we use for these recommender system matter a lot. And one of the key factors that influence the training efficiency is exactly this memory capacity, and also how do we reduce the memory bandwidth requirements across these CPU and GPU trainers.
Okay, 2 more questions. How about the speed up on mobile settings, mobile CPU, edge GPU, and edge TPU?
For recommendations or across the board for different DNA use cases?
Why don't you answer the question that you want to answer?
Sounds good. So what about speed up across the different accelerator? Okay, so let's see. Something I would like to highlight from the HPCA 2019 paper is that, and that's actually one of the reasons that brought me to Facebook about 2 years ago, is I was working on energy efficiency optimization for smartphone type of edge platforms for quite a while. And we all know that there is all these like mobile GPUs, there's a DSP, and they are various different kind of neural processor accelerators that making their ways into the SoCs, right? So my question the question I wanted to answer 2 years ago is, we all know that machine learning is happening. We all know that machine learning inference is running on at the edge, but like, do we actually leverage these mobile accelerators? Like, do we leverage these general purpose accelerators on smartphone chips, right? And I was, and this is summarizing the HPCA 2019 paper. And I was kind of surprised that they are not. And there are some key reasons for why these GPU or DSP general purpose accelerators were not used. One of the reasons is because if you look at the performance ratio between mobile GPU and the CPUs, it's very narrow. Only about, like, if you look at all the smartphone devices that runs these Facebook app, for example, only about 10 to 15% of the smartphones have a GPU whose performance is 10 times more than the CPU. That's what the mobile landscape look like. It's very different from what we are used to when we look at the desktop or server setting, where GPU is way more performant as compared to the CPU. Okay, and it's not surprising after looking at the data. It's basically because these mobile GPUs were not designed for high performance computation to start with, right? And neither is DSP. So first is that the performance ratio from the hardware perspective, if you only look at the theoretical performance ratio between CPU and mobile GPUs and the DSP, it's quite narrow. And secondly, the software stack is kind of broken. It's actually really hard to, say, write a acceleration kernel using OpenCL. Like oftentimes when we try to offload these machine learning inference computations on the mobile GPUs, we found that sometimes this is going to cause app crashes. And if it crashes only 1% of the time, that already translates into hundreds of millions of users, right? And so that wasn't the kind of trade-off that companies like Facebook or any like large mobile app developers can take. And so that's another sort of limiting factors for why it's very hard to leverage these general purpose accelerators on the smartphones. Things might have improved over the past 2 years on the programmability aspect. What I can say is also that on the AR, VR type of system where the hardware and software can be better co-designed together, there is definitely more acceleration opportunity using these general purpose accelerators. But it's just hard when we look at just the smartphone landscape.
Okay, 2 more questions. These are by Young Yang. For tensor decomposition, can we do architecture searching latency optimal decompositions for recommendation models like Google mobile DETs?
Interesting idea. I think the quick answer to that would be it depends on the size of the design space or the search space. So for one, the most recent work that we are looking at in the tensor decomposition domain, we are looking at, for example, the embedding vector dimensions, and we are also looking at different tensor ranks. So depends on how big this search space is, we may be able to come up with a simpler search algorithm instead of using a more elaborated approach, as I think what this question is suggesting.
Okay, final question. For autoscale, is it using architecture search to achieve performance improvement like Google, MassNet, or EfficientNet?
So on autoscale. So what is autoscale doing? Autoscale is basically looking at the kind of setup this is what we call the edge cloud collaborative execution environment. And so an example of that is, for example, we all know that tons of efforts is getting into the development of, say, VR headset. And so like these Oculus Go, different versions of Oculus headset that we can buy in order to have different virtual reality experiences, right? One of the very early version of these Oculus devices required the device to be plugging into the wall power on the wall. But then really, like, going forward, we don't want any wire connections. And what this means is that the kind of chips that goes into the headset has to be extremely low power. Now, how do we still be able to provide rich user experience? So we can imagine that some of the setup is going to be backed up by a staging device, let it be your smartphone, for example, and that smartphone or staging device can have access to power sources. And that can be further backed up by all the servers in the cloud. Let's imagine that's the edge cloud execution environment like, okay? And so now when we have such a setup, and you can like imagine there's all these like Apple Watch, all type of wearable devices. One of the scheduling problems that we'll have to solve is which computation, which part of the neural network, what type of neural networks, if we are leveraging different neural networks to help us make better predictions. How do we schedule these neural networks onto these cluster of systems that come with different system architecture, characteristics, power performance profile, and while also maximize the battery lifetime of your wearable. And so that's what the kind of problem that AutoScale is trying to solve. What the research community hasn't really looked at is this unique aspect of stochastic varying factors. So when these devices are connected with each other, the kind of experience that user is going to feel is, network stability, for example, right? So how do you then make your computation scheduling to be aware of these varying network strength, which is going to affect your offloading performance? And then there are also environmental factors that can affect execution performance on your wearable device. And so that's when this reinforcement learning algorithm comes into play, is basically it learns the network strength and the interference on device effect on the execution performance. And then it basically decide when and where to offload these neural network computations.
Okay.
And so it's kind of a different type of problem as what the Google's NestNet is trying to solve.
Okay, great. So I'm going to give Carol one last applause, and then Mark Mancy can end the recording and we'll wrap up. So great talk.
Thank you, Mark.